Good morning. Last week I realized there was a little technical issue in my presentation, so I lost the last piece of the first part in the morning. I recorded that, so you have it as recorded lecture. That was why I was so confused when it all of a sudden stopped, because somehow the lecture skipped something. That part is now, as I said, recorded, so you have it. It's also in the lecture notes. I'm sorry for that technical mistake. And, well, that brings us to... first, are there any questions about last week's lecture? No? So then we can go on with the advanced segmentation. So last week we talked about more looking at the histogram, problems determining information from, for example, radiographs, seeing that there can be a lot of ambiguities. And the missing part was actually how you can select a segmentation by looking at the histogram, seeing that there were two bumps modes in the histogram, and by putting a threshold between them, you can do a quite good segmentation. But that is manual work, and we don't want manual, in particular not when we do many images. We don't have the time for doing manual. So let's see if now it's alive. It should be on the right spot. Doesn't move. That's strange. Now it comes. Yeah. So we have also a lot of different kinds of samples. There are samples which are not very easy to segment, and in particular not using the single threshold. So I'm going to go through different methods, how you can do segmentation. And the first part, is more the traditional way, and the second part is more towards machine learning based methods. And of course we have a lot of modules that we need to load, and now in particular we start using a package called scikit-learn for our analysis, and that comes of course together with scikit-image and also pandas. So, well, actually I talked already a lot about these. Important thing which is still relevant is that we can be filling holes. So we have seen already that when you have two overlapping classes, that you get more or less amount of misclassified pixels, and with the help of morphological operations we could actually fill the sum of it at the cost of maybe some edge modifications. So, looking into segmentation tasks, there are very different types of segmentation we can do, and actually also classification. So this is these are 4 different examples. So one is image classification, just telling what is in this image. That you probably know from your own picture gallery, that you can even search for different characteristics, specific persons if you have trained it to do it, or just say I want to have pictures of food, and it gives you a collection of pictures with food. Next step is to localize object, and then it's not about the exact contour, but more about boxing it in the image. It's a quicker way to identify objects, so it's often used, for example, when you do look at videos of cars on a road. Then you only need to know where the car is moving, not exactly what it looks like. But in this case, we even have categorized these different regions, so we know that the blue ones here are sheeps, and that one is a man, and then we have a dog. The semantic segmentation goes a little bit closer, so you really frame in to exact contours of these objects. And then you can again see we have a sheep here, and the man is turquoise, the whole contour is filled, and we have the dog in the corner. The last one is instance segmentation. Then you actually can identify the individuals in this image. And more reading about that you can find in this Lin et al. Paper. But these are the typical categories we are talking about. Today we are actually not even going into all these categories yet. That comes later. But what we like to do is actually extract one type of relevant feature. There are also problems when you try to do segmentation. This is, I think, a wonderful example of that. When you look at this painting, what you see at first is just the fox in the middle. You see anything else here? There are actually 2 horses and 2 Indians. So you have one horse here, one pony, and the rider on top. And then you have a second horse here, and that rider. And that, I think, is a very good example how information can be obscured by other features in an image. And the trick is really to find the things you are looking for. So let's go on. Here are more, say, technical view of that problem. So I already mentioned all the things about artifacts and noise and gradients and everything, but what is the actual effect of it? So if you look at an image with artifacts, you can see that the histogram of that one should in principle just be 2 nice peaks. But thanks to all these artifacts, you have a very overlapped histogram. It's still on the same level, so when you try to segment it into 2 classes, you see that you have misclassifications outside and misclassifications inside. And that is one thing, that the artifacts can obscure things. Next is if you are unfortunate and get a very low signal-to-noise ratio, you can also see that the histogram doesn't even show that there are 2 different classes. These peaks at the end is just because I truncated the histogram when I computed it. So actually, they are the long tails of this distribution. And when you try to segment it, well, you essentially don't get anything. So this is a typical case where you would put in some denoising. Same is for the artifacts. The denoising would probably help you quite a lot. A trickier thing is when you have gradients in the image, like this, then the histogram looks pretty crazy, actually. It kind of gives you 2 classes, but they're not really what you want. So if you try to segment this one, you actually get, of course, you get these disks, right? But you also get a frame around them, which has the same intensity, and that is not really what we wanted. And of course, we have also noise combined with unsharpness, and that can give you a very fuzzy contour of the objects. And an interesting observation here is that with increasing blurring, you actually increase the height between the 2 peaks. So with only noise, you would have 2 widened peaks, but as soon as you get blurring, the area between the valley between them also has a lot of gray levels, and that is something that provides you also with some uncertainty in the segmentation. And then we try on some real data. This is actually a little bit synthesized because I just added some different intensity levels, but you have this cell colony with different illuminations, and if we try to segment these using the same threshold, we get into trouble. So here I set the threshold 0.6 because that was good for the first one and we got some nice results. However, when you have a darker image, you see that this 0.6 gives you a lot of over-segmentation, and particularly in this corner because we had this gradient I mentioned last week. If it's too bright, then you get under-segmented, so you miss a lot of these cells. And yeah, well, so on. It goes on to different values here. And you can see how the volume fraction varies depending on the illumination. So you need always to have a good illumination, or at least normalized, to get the same basic distribution of the intensities. So let's look into some tricky cases. Here we have a bone slice, and we want to find the larger structures. And then we also want to find the smaller channels between them. And the first one is kind of easy, because we can, here we can first threshold, and then we can use a secondary criteria about the size. Measuring the size is, however, something we are not going to talk about today, but I think next week. The other one is these small channels. They are really so small that we have problems with blurring and partial volume effects and also noise, and they are much harder to identify. Another one is finding the brain cortex, which is barely visible to the human eye. And also there are very tiny structures that hint on where this cortex is. So now a simple threshold would not be sufficient to be able to find it. So we need to do some smarter things. And just applying a single filter doesn't really work either. So doing a low-pass filter would just smear out whatever there was that could even indicate that there is something. A high-pass filter, putting some gradients, possibly, but still, there are so many structures that this one is really a tricky one to segment with traditional methods. So we can just try putting in some thresholds here for different regions, and you see that, well, you get you almost get this in layer, the regions, and these don't make sense at all. This task of setting a threshold is a very common task, and there are also very many different ways of do this automated to do it more reproducible. In the tool ImageJ, if you know that, there is, as you can see here, a long list of different ways to put the threshold depending on the characteristics of the data. And well, you can just click and test and see which method would be the right one for you. You can also read in the manual and see already which one does more sense to you. For example, see, yeah, there is, for example, this ISO data, intermodes, and OTSO. They are made for having two classes, clear classes, more or less same distribution. If you look at the triangle, for example, it's more if you have very large data imbalance in the data, so you have just some few pixels on the tail of the histogram, and then the triangle can help you there. But there are quite many different types, and you have to look into your own data and see which one matches the best. So we have the histogram-based methods, which in principle was what ImageJ here showed. Some example, as I already mentioned, are also ISO data and intermodes. Then we can look at image-based methods, where we look at different statistics in the image and try to adapt the thresholding in a way that these features really appear. Result-based is we are segmenting objects with a certain size, and that requires that we measure the sizes of the objects. But let's say you segment the objects you want. In this case, example is about cells, and the cell size should be between 200 and 10,000 pixels large, and that is what the algorithm will look for. And then it tries to optimize iteratively until it finds these objects. So, looking at the histogram-based methods, again, we look at this bone cut, and you see that this histogram is not very easy to put a threshold on. So where should you put it when you have just a single mode? And you see here there are some darker regions, but they don't really appear well in the histogram. Possibly there is some bump, and there is a tiny indication that there would be something around here. So if this data wasn't cut in the way it was in the gray levels, you see this very high peak, you would probably see a little bump over here. But this is the way we got the data, so this is what we have to work with. But I would say a first attempt would be to put the threshold somewhere around between, I would say, 0.1 and 0.2 and try as a first attempt on that. But let's first look at a toy example on how the segmentation works. Now I'm going to talk about the histogram-based methods. And the toy example is just that we have two regions, one with a high intensity and one with a low intensity. And if we plot the histogram of those, you see as blue here is the global histogram, but looking at the histogram of each one of these, you can see that there is a little overlap in between, and this is actually the uncertainty, or tells how uncertain our segmentation will be. So let's try and see what different methods do. The intermode is a very simple method. Actually, it requires that you have two clear peaks in the histogram. And what you do is you measure the average distance, or the distance between peak 1 and peak 2, and take the middle value between them. And that gives us a threshold. And, well, it gives us something. We have some misclassified pixels. And you can also see that the threshold here is actually landing in a way that the bright pixels will have some misclassifications, that part. And the dark part will have more misclassified pixels, which is this part. So you can already see from the histogram, when you put the threshold, how much you will have misclassified. This is the best we can do with that method. And looking further on, we have the OTSO, which is a classic algorithm. I would say mostly this is the first go-to method that people use when they try to put the threshold on an image. It's more statistical approach, so it tries to minimize the variance within each class, and the variance between the classes should be maximized. And then from that, there is a cost function, which nicely have a maximum at the point where these classes are best separated. And interesting is, in this case, we get about the same place for the histogram for the threshold as with the intermode. You can see it's just slightly below 0.5, which we also had here. The next method is isodata. It's a little bit more algorithmic. It's an iterative approach where you look at the starting with a threshold guess, which is the maximum intensity, the average between maximum and min intensity. And that's our starting point. And then iteratively, you refine in a way that you get you do the segmentation. Background is less than threshold, object is greater than threshold, and then you compute the average for the background and the average for the objects, and again take the average of that. And when you iterate, you see here the dots, the height of the dots is the iteration. At some point, you don't have any change anymore, and that's the end point, and you can see that it relatively quickly converges towards a threshold, which again is something slightly below 0.5. And again, we get also this kind of segmentation. So all of these three methods, for this case, produce the same result. It could be, if you have more complicated histograms, that things can be more tricky. If you look at the code that I used to generate this, I did a little mistake, because when I computed this background and foreground, I used the whole image, which is inefficient. I could just use the histogram. But at the time when I did it, I just did brute force. So you could make this thresholding a bit more efficient. But it works like this. So these were only some few thresholding methods, and there are many more. So there are different image processing packages, OpenCV2, scikit-image, and each one of them have a big catalog of different thresholding methods. And if you, for example, in scikit-image, there is even this try all thresholds function that goes through all the threshold functions and shows you original, and then it shows what each of these methods produce. You can already see here that the performance is very different between them. And I would say that the Lee is probably a method that is targeting the tail distribution compared to isodata, which we already saw, which puts quite good thresholds on larger areas. The mean is, I guess, just the mean value that they use as a threshold. That's a way to do it, but probably in most cases not very relevant. And now I can't scroll, but I think there are about 4 or 6 more different cases, which you can see in the lecture notes. But it gives you at least a catalog of all these methods, so you can get the first idea what each method can give you. So this is a quite useful function, and yeah, you can just try it out when you have your images. So there are, of course, problems with setting as just a threshold. The histogram-based is very sensitive to how well you can measure a histogram, how well separated it is, if you can actually have some bumps that can be identified with the actual method. So that can be tricked out if you have bad data. The image-based one is also sensitive to signal-to-noise ratio, and statistics if it's very sensitive to how the statistics change in the image. Then the result-based, well, that one is, first of all, biased by your initial hypothesis, what you actually said, or the constraints you put on the thresholding. So if you say you want between 200 and 1,000 pixels, you will get those items no matter what they show. So if you have other objects which are not really relevant and they fall into this category, you will get them too. So there you have to be careful and actually check that it actually finds the right ones, or that you have clean enough data to be able to actually pinpoint those objects that you want to have. Then we can also have some more approaches to handle this. We could try a model-based approach, so really trying simulated, including noise, and see how well these methods work. And then we come back into the test procedure that we need to really test and verify. And then we can put on also some statistical constraints, looking at quantiles and seeing if 95% is hit within this category, then we could say that it's good. Then you can also apply the methods to each one of the samples and see how it changes, or more or less adapt for each one. And then we can try that way. Worst case scenario is not shown here, but there you also have to go into more statistical approaches and say that you have to reject when they are not statistically sane. So you just take the middle quantile of the results. So that's a fallback version, but I would say the worst case, then you should probably rethink what you had done and instead try to find a better method. So we saw before, when I showed the tricky cases, that with blurring, you can get very uncertain edges. And you can also get maybe, you have some uncertainties in the selection of thresholds. And a single threshold may give you a lot of misclassifications for smaller regions or for some that just barely go above the limit. And for that, we can think about a different approach where we use actually two thresholds. One, very strict, where we're assured we get the structures we want to have. And the other one, it's a lower one that gets the full boundary. And here you can see an example where I put two thresholds. I put one, a strict one, which is very close to the peak, and one less strict. And you can see in the green, I get all the full region, but maybe I miss some relevant features. And then when I go to the yellow one, I get a lot of misclassifications, which I don't want to have. So let's see what we can do. Here we have, the Goldilocks situation. You know, the little girl that comes to the house of the bears and find different things, and in the end she selects the one bed that suits her, the porridge which had the right temperature or the right size and everything. This is essentially the same thing here, where we put two thresholds. So we put a threshold here, in this case at 70, and one threshold at 110. And you can see that in this case we may get a little bit too little. You can see inside of this you don't get all the whole object. If you set threshold so that you get the whole object, then you have to have a lot of misclassifications. So what to do? First we do these two thresholdings. In the generous threshold we may do a lot of, in the strict threshold we do some cleaning, so we could do maybe some opening operation just to remove small misclassification that still were in. And then we take the strict one, the higher value. The less strict one. I think it's a little bit flicked here now. And then afterwards, you combine the two images and use region growing from the small regions out to fill up the larger regions. And this looks like this. So we have the strict threshold, and you can see there are some misclassifications. We do the opening, and you can see that it's a bit cleaner. There are some still remaining, but let's keep them. Then we have the looser threshold, which have a lot of misclassifications, and then we combine them. And we do the region growing from this one into that one, where the regions overlap. And finally, we get an image that looks like this. So then we have actually the best of the two worlds. We for example, have filled the whole of this one is filled. And we don't have all the misclassifications that you will see around here. So with that, we have a more robust threshold for our continued investigation. Another trouble that we have when we put thresholds is when we have multiple classes. And when we have a case like this, again, a toy example, box in a box, with some blurring along the edges. If you look at the histogram, the natural places to put the thresholds would be at these places. So 0.6 and 2.2 I have chosen. And the problem then is when you do this, you see here that you get some kind of skin. And we don't expect this skin in reality. It should be the high intensity going straight into the background. So this virtual skin effect we need to get rid of in a way. And first we just want to see why it appears. So what I did, I took the line profiles at different places in the image, I plotted them here. So you can see the green one is stepping from background into the middle level. Then you can see that we nicely go from one level to the other. I have the orange one, which goes from the bright into the middle level. That's also fine. That also is classified correctly, so there is no skin. But the problem comes when we have this blue line, which goes actually from the background all the way into the high intensity region. Then you see it passes through the orange region. And this is where the skin appears. In particular, if you have a lot of blurring. So what you get then is when it tries to go from the dark, it passes through the orange or mid region, and there it produces 1 pixels in the middle class. And then it goes on to the highest intensity class. And well, this is the uncertainty we have with the blurring. And now we need to find a solution how to handle it. One way is to use some kind of hysteresis to avoid it, or as I show here, a more algorithmic way. We identify regions which we need to guard, so around the edges, and then we exclude them from the first thresholding. So how to find this is just to compute the gradient magnitude, and then you can see that around these edges we have a very high gradient, and along the other edges it's much weaker. So if we then threshold, so we can get this guard region and say put this one aside and then do the thresholding, and afterwards in this region we can do region growing from the dark into the guarded region, and region growing from the bright into the guarded region. And when these two meet, then we get a nice segmentation near this edge. So this is one way of doing it. There are certainly many more, but this is an approach that has quite good success in many cases. So it can be even more complicated. We have images with multiple data on each point. So for example, if you have a color image, you have 3 color channels. You also have MRI images that have different information going more into the spectral imaging. You have the Raman shift, which actually produce a whole spectrum behind each pixel. And when we want to look at these images, we have to also introduce maybe more complicated methods for the segmentation. Then a single threshold is a bit tricky, because then you go into some multi-dimensional space. And for that, I'm going to show you now a couple of cases that, or methods that we can work with. One way is actually also that you can import, extract more information or add more information in order to help the segmentation. So in this case, you see a picture of some text, and you can see that the illumination here wasn't very good. It was probably some shadowing from the lamp was coming from the wrong side, and the book was a bit bulged out. So you get this gradient. And trying to put a threshold on this is very tricky. So what we can do is we estimate the background like this. And what I did in this case was just subtracting a very wide Gaussian filtered image. So it blurs every text. And with that, you get the trend in the image. And you subtract that, and you can see that you got a much more flat result, and that's easier to segment. So let's take this image and convert it into some table, and just to see what we have. We have different pixel positions. We have the intensity, and in this case, we even have a label if it is text or not text. This will help us to analyze the situation. And if we create a histogram of the class is text and the class is not text, then it looks like this. You see that the gray levels are very much overlapping, and that's not very nice when you want to try to put the threshold on the data. So what can we do? First, we look at the ROC curve. Looks actually pretty good. Not fantastic, but you see that you have a nice bulge, so it tends towards the 0-1 corner. So it will do some segmentation with some accuracy, but it will not do it perfect. So let's add some information. In this case, we will do the difference of Gaussians. So we have here, we have two Gaussian filters, one with a wider one and one which is a bit more narrow. And the difference between them actually produce a kind of a bandpass filter. So let's try it. Oh, that's strange that that one came in like that. Okay, yeah. Anyway, we have this function that I had defined for computing this filter, and let's try it on the data. Then the data looks like this. So you remember from the previous case that we had the isText went all the way back here, but now we have a much more narrow histogram for the text, which looks like a better situation to segment. So let's see what happens. If we look at the ROC performance, this filter action actually brought us to much better performance in the ROC curve. So we moved from this one to that one. That means we will, with better certainty, segment the text in the images. So why it now performs better is actually that we have these two histograms. You see that there is a lot of overlap, much less overlap, and this difference is that what actually creates the improvement in performance. So, so what we learn from this is, in principle, that by applying some extra filtering, you can improve the segmentation performance quite radically. It doesn't have to be just a single denoising filter, but it can also be something that, of a global scale, improves the illumination and homogeneity of the data. So, next step is we go into a different kind of segmentation, and that's using clustering. And now we have, instead, we look at the pixels in a more automatic way. And let's start with some very simple example. We have these blobs, and we want to separate them into different classes. So this is not, right now, not images, but we can come to that. And for that, we're going to use a first attempt. We try using an algorithm called k-means. I'm going to explain that on the next slides. But by using this k-means, we say we want two clusters, and the algorithm actually finds two clusters out of this data. And the result is then coming in here in the table. We can see that Some coordinates, they are classed into group 0, and some others are classed into group 1. So this makes sense. The algorithm as such is an iterative, self-stabilizing algorithm. So you start with the unclassified data, and actually each pixel or data point gets a random class assigned. In the next step, you start updating class statistics. So you take all the pixels belonging to class A, compute the average. You take all the pixels belonging or points belonging to class B, compute their statistics. And then afterwards, you reassign the classes, looking at each pixel or point, and see which one is it now closer to. So you have these original averages, and if a point is closer to that average, it will be assigned to that one, and the same in the other class. And then it iterates until stability. And it actually goes pretty fast. I think within 5 till 10 iterations, you have a stable case, and with that, you have your classification of these data. So let's try k-means with different clusters. We have 2, 3, 4, and 5 clusters and try on the data. So if we do 2 groups, you see that one makes sense. We have a nice separation between that one and that one. With 3 groups, it also makes sense because this could be actually a clear blob and that one too. So we get our 3 nice groups. But if you start doing more classes or more groups, then you see that it's getting more and more constructed. So it says, okay, this one would be the group 4, apparently. And if you do 5 groups, it's really crazy. So when you use the k-means and you don't know how many classes you need, you may have to run a test like this. In some cases, you even do too many, and then afterwards you do a class merge. That is also an approach that can happen, that you can do. So, and then we can even add more vector spaces. Right now, we are only looked at some x and y coordinates and the pixel values. But what you can add, or actually, if you have an image, you actually just look at the pixel values. But you can look at positions, you can look at some other metrics that you can want to introduce into the data or into the classification. So in this case, we created some different extra information. So we would have x and y coordinates, we can have a weighted neighborhood, we can look at edges, and with that we can try to add more information to the classification. So this brings us from, in the original case, that would be just a one-dimensional classification. And then here we got into a 6-dimensional feature space, which needs to be found a minimum for. Actually, a little comment is that k-means, when you do it on a single image, is essentially the same as if you would do Otsu's segmentation. So let's try. We have the coordinates for each pixel and their intensities, and we try to run it. And the output, saying we want 4 clusters, is, whoops, that one. Not very convincing. So what happened here is, if you look at the data vectors, you can see that the coordinates, they have a much wider value span than the intensity, and that makes gives the coordinates much higher dominance in the finding of the clusters. So what we need to do is to look into a normalization or scaling, actually. So we have to scale by a factor 10 and bring in the intensity. And if we try that now, let's see, I think I need to go back. No? Oh, shit. I need to go back even further. Sorry. Oh, okay. Sounds like it's time for a break. Uh, okay, so let's take a break and we continue afterward.